This is Team 11 with our final DS Lab project presentation. And our presentation has the problem of predicting the winner of a UFC fight. So UFC is an MMA organization that hosts MMA fights. And usually there are two fighters that can win either by submission, knockout, technical knockout, or decision. Why this would be beneficial to predict is we can bet on these odds. So betting on a winner, we can gain some monetary value from predicting the correct fighter for upcoming UFC fights. And so we collected this data from a website called ufcstats.com. We used a web scraper from one of the sources below and scraped about 5,206 fights with 46 columns of data. This data ranges from the individual stats of the fight, some post-fight stats, and some of the pre-fight stats of each fighter. So as you can see below, we have Sergey Pavlovich. These are the individual attributes of height, weight, reach, stance, and date of birth. And then here are some of the career statistics. So strikes landed per minute, striking accuracy, strikes absorbed per minute, striking defense, takedown average, takedown accuracy, takedown defense, and submission average. And of course, this data indicates that this fighter is more of a striker than a grappler. Thus, we can interpret that there may be some interpretation to this data to determine who could potentially win this fight between Sergey Pavlovich and his opponent. So when we obtained our data, there was a lot of data pre-processing that was necessary, lots of categorical features and lots of features that were either objects or strings, and we needed to convert all of these into numerical values. So for the categorical data features like weight class and stance, we decided to use some one-hot encoding to map those strings to some numerical values. For the objects and strings, like the record string that was in this format, we decided to break this feature down into wins, losses, and draws, and decided to neglect no contests as they are very random and difficult to predict. From the date of birth of fighters, we calculated the age of the fighter by getting the difference between the date of birth and the event date, just to get an estimation of what the age is for each fighter. For the height, we had to convert the string of feet and inches to just inches by doing some simple mathematics. And then we dropped all post-fight stats, event date, event time, fighter names, winner, win method, and win finish, round, and time, since these are all post-fight statistics that provide no value to predicting who won the fight. In the end, we narrowed down our features from 46 to 33 features that are numerical with no objects or strings. So we decided to analyze our data. The first thing we did was we found the correlation for each feature in relation to the winning label. This winning label is either 0 or 1, 0 being that fighter 1 wins, and 1 being that fighter 2 wins. And so you can see down on this correlation heat map matrix, the darker shades of red indicate higher correlations, while the lighter shades of blue, or darker shades of blue, indicate the least correlation. To make it easier to view, here we have the individual statistics. So fighter 2 strike landed per minute and fighter 1 strike landed per minute have similar correlation to the outcome of who would win the fight. And as you can see down here, the weight doesn't really matter, as typically the fighters will be around the same weight in their respective weight class.
Right. So for feature engineering, we just decided to create different permutations on the data set, on the process data set, to see if we can improve the scores of like accuracy or AUC score by either adding new features or removing some features that we might think is insignificant. So first, we mainly categorize the features into two classes. One of them is rate stats, that includes stats like strikes landed per minute, takedown average, submission average. So these are like the stats that has like number of actions. We also have rate stats, which are like, or I'm sorry, we have percentage stats, which are just percentage stats like strike accuracy or takedown accuracy, takedown defense. And some of the permutations we made start with dropping the features that we might think is insignificant. For example, weight, because every UFC fighter will try to reach maximum weight in the weight class. So we thought this would be one of the insignificant features. Also, like how we categorize the two classes, we tested to see if one kind of stats yields a better result than the other one. So we tried dropping all the percentage rates, all the percentage stats, and all the rate stats to see which one, to see if one or the other carries more weight. We also excluded height because we thought reach alone could be a more important factor than adding height and reach together. We also created a new feature, created a new column called win rate by dividing the number of wins by the number of total fights. That is the sum of win, losses, and draws. so that our models can better account for outlier cases, like when the fighter has like low number of wins but like he's undefeated. We also try to see if striking only or grappling only stats would yield a better result. And we also tried the differences in the stats. That is, subtracting fighter one's stats from fighter two stats for all these different stats. We also tried combining number 10 and 11 to see if that works better. And after the 12 attempts, we determined that attempt 7, which is to add win rate, resulted in the highest accuracy in AUC. So with the result from that, we tried some more modification that includes attempt 7. Like we added win rate, and then we also dropped records, because dropping records was also another high-performing permutation. But that actually did not result in a better accuracy than just adding the win rate alone. So with the different feature engineerings that we tried, the best working one was to add the win rate that we calculated in the features.
Yeah, so like now that we did the bulk of our project was mainly just pre-processing all the data sets and coming up with like the different permutations of data sets. Now we can just throw like all the different permutations into different models. So the models that we used was like logistic regression, gradient boost, ADA, decision trees, random forest. And after like some of these models, we saw that the accuracy and the AEC scores that they gave us weren't given like the best score. So uh, in the final project, we ended up taking a couple of models such as like random forest, K neighbors, and a couple others. And if you look at the this graph, we plotted all of the results of running all the permutations for each of the models that we ran. So you'll see the scores for like logistic regression, gradient boosting, ADA boosts, etc. And if you look through like the different subsections, you'll see that can you scroll down a bit? Yeah, so like for instance, we have like all the results for logistic regression and all the results for ADA boost. And like Joonha said previously, we ended up seeing like the best AEC scores and accuracy scores were generally the win rate permutation, but other notable permutations include drop rates and rate difference for the best AUC scores and drop rates and percentage difference for the best accuracy scores. And overall, we saw that the best model for our permutations was stacking classifier, but cat boost was also like a good model that yielded us the best results.
Yeah, so the reason we decided to kind of take an approach to the deep neural network was because it has a good reputation for modeling complex relationships between specific inputs and output values. Additionally, DNNs are also kind of really good at learning hierarchical representations in data, and so it would give us a good weightages for the different attributes that we were trying to look for, and it would overall just give us save us time on the feature engineering aspect. And so in our particular case, we ended up using a Keras sequential model from TensorFlow to build the neural network. And using this model, we were able to receive around a 70%, which was pushing us in the right direction. So using that neural network was actually not a terrible idea to do. And then moving on to ensembling, Johnny mentioned before that we tried using ADA boost, log regression gradient boost to attempt to try to get a good score. So what we tried to do here was implement all of those different models and trying to get the strengths and weaknesses of those and make that into a final model prediction. And the way we did that was we used like a hard voting system where each model gave like a single prediction for what it thought it would do, and then based on those predictions we would see like the mode, which one was the most for the prediction, and that is what we would use for our metric for the ensembling. And ensembling kind of gave us a higher score. It gave us like a 73% I think prediction accuracy, so that definitely moved us in the right direction.
Yeah, so now that we found which data set was the most impactful one, which was adding the win rates, by seeing like how all models did across all data sets, we were able to determine that adding win rates was the best one. And then we ran all the models throughout all the data sets, and we found out that stacking was the one that gave us the best results overall. When we removed stacking and voting classifiers from it, we see that gradient boosting was the one that was doing the best amongst the normal models. So therefore, we use gradient boosting as the final estimator in our stacking classifier. And then we got into hyperparameter tuning to try to improve our accuracy. For hyperparameters, we essentially changed the learning rate, number of estimators, and max def, and put them into a grid search in order to figure out which were the best results. And it came out to be the learning rate of 0.01, max def of 3, and 100 estimators gave us a 0.8 accuracy.
Okay, yeah. So in conclusion, we used a variety of data science principles, including feature engineering, different machine learning models, adjusting the hyperparameters of those models, and various ensembling techniques. And we ended up achieving around an 80% accuracy rate. And we believe this is actually relatively successful because it's reasonably capable of determining who's going to win the fight, and it substantially outperforms a coin flip probability, which would be just 50%. And we do acknowledge that UFC fights are influenced by so many different factors, and we would need a much more comprehensive data set to give us more accurate predictions than the 80%. But given the allotted amount of time and other factors, we believe that our accuracy rate is rather satisfactory for this given project. And in conclusion, we know that artificial intelligence has had a significant impact on the sports betting sector in recent years because of its ability to extract insights from large amounts of data. And talking about some of the problems we faced while developing our model, I guess one of our largest challenges was from the fact that the data was given so that fighter one's features would always be the winner's feature. So the data itself had fighter one winning every fight. And we had to fix this issue by swapping the fighter one features and fighter two features of every other row in the data. So the winners of each fight would alternate, and thus like no particular fighter's features would be biased. And another solution we had was to calculate the difference between each feature of the two fighters. So we had relative data rather than the given raw data from the original data set. And in the future, with more time, we would like to aggregate more features such as the overall fight time and the strengths of each fighter's previous opponents reflected in his or her record. And we would have to get a different data set and do further data feature engineering to do so. And we are aware of the limitations of using a limited amount of features to predict an outcome in sports betting, just because there's a lot of different factors that can determine an event's outcome. But that being said, we believe that the model that we have created using different permutations of comparisons between multiple entities has value in different real world scenarios, including the stock market and the continuous aggregation and resulting availability of data sets in the world in general will allow for the further extraction of insights in various applicable fields. And that concludes our team's video presentation on our project in correctly predicting the outcomes of UFC fights.